Okay, so this is DSC40A, which is Theoretical Foundations of Data Science, which is really a Theoretical Foundations of Machine Learning class, which is really kind of a random assortment of math and how it applies to machine learning. So it's a pretty good class, and it's going to test your guys' skills kind of with linear algebra and probability. But it will set you up nicely if you stick with it for a lot of the other classes that HTSI has you taking, specifically the 140 series. That being said, I put a big post on the Piazza about how this class will run this summer session. So we'll do Tuesdays, sessions in class, plus have a recording that we'll put online. And Thursdays, we won't meet in class, we'll just do office hours, and then we'll put additional recordings of the Thursday section stuff on YouTube and put links onto the website. I try not to make too many announcements in class and just keep it to Piazza since everybody will be able to see that, hopefully. For today's class, we're going to do the introductory lecture, which will kind of set things up for how we're going to be studying optimization problems over the next 6 weeks. And then we will transition. This lecture is usually like an hour and 20 minutes, but I'll try and finish it in like an hour or maybe a little bit less. It's nothing like really heavy mathematically, but I don't want to be here for 3 hours because it gets kind of difficult sitting here for 3 hours doing math and stuff. And we have a complete linear algebra bootcamp prepared after this with me and a bunch of our course TAs behind you who will be kind of walking through what you should remember from linear algebra in order to do this class. Which is about half of Math 18. So we'll try and get through a bunch of it. And I have a large 25-page linear algebra bootcamp packet that Owen and myself put together that we will be using today. And then we will provide that for you sometime tonight, early tomorrow morning, because there's a few changes I want to make and clean up some figures. That should give you guys a good roadmap for what you should have remembered from Math 18, which usually is not very much. I took Math 18 when it was 20F at UCSD. So what I remember is not very much either. Linear algebra is one of those things where you want to go through it a few times. So that's what we will do today. Okay. So my name is Kyle. I was a UCSD undergrad and then a grad student at UCSD. I'm probably a little bit of a rare bird at HTSI because I'm maybe one other faculty member who just teaches part-time. I mostly work in industry. I've been working in data science since 2013 in all different facets from junior data scientist all the way up to the director of data science. So I have a large knowledge base of how to do data science. But I really like teaching. I like working with students, and I think it's a lot of fun. So I've been doing this for about 5 or so years. We have a really great selection of TAs behind you. So that's Owen, Jason, Reed, who's our guest TA. Who's an old TA for me, but he works for me full time, and he wants to catch up on some linear algebra stuff. So he's going to have some fun. And Nick, and then Varun and Jakub are our other 2 TAs who aren't with us today. They're remote, so they will be working remotely for a little bit with us. Yes. This is my journey. Try and go through this stuff a little bit quicker. You can always read those if you care or ask me any questions. Course staff. Skip this. Okay. So. Hopefully you've all read the logistics post on Piazza. If not, please read that post that I made early this morning. It will tell you how the whole class is run. And feel free to respond to that post with any questions you have, and we will answer them. But I feel like it might be better to dive into it right now. So Theoretical Foundations of Data Science. This is a class that a lot of people would probably say is the hardest class at HTSI, or in the DSC degree. I don't think it's the hardest mathematically. I think there's other classes that are more difficult in terms of the stuff you do. But this tends to be less difficult because for most students, you haven't had very many difficult classes yet that challenge you in the way this class will challenge you. And so I think it's kind of like that first exposure to a class which asks you to take a bunch of mathematical concepts that you've learned over the last 5 or 10 years of your life and incorporate them into solving problems. And that's a very difficult thing to do. And some of the problems that we ask are very high-level problems that require you to really think about what it is that you're trying to use math to help you solve. Like, what's the problem you're trying to work on? Not so much like a 1 through 50 odd problem where you have to, like, solve for X or do something like that. These are more like, here's a story with a bunch of information. What do you know from your math background and from the things that we've learned in class that you can use to solve this problem? And those are much more difficult problems, but they wind up being more akin to the types of problems that maybe not mathematical problems you'd solve on your job, but they're more like the types of problems that you would negotiate in a real world setting where you don't have all the facts necessarily, or you have imperfect knowledge, or you have to go look up stuff, things like that, where it's not quite so known how to start. So that's what makes this class kind of difficult. But it's really important that you take this type of class because, for example, when data science first started, there's a reason why the majority of people from like 2012 until 2018 had PhDs in neuroscience and physics or master's degrees, is because the kind of problems that data scientists typically work on, if you take like the original term of data science, is problems that you learn how to tackle by going through a PhD program where you had to go do your own research, you had to go explore ideas, find information, gather it, come up with hypotheses and test them, and do all these type of things. So it's a very difficult skill set to learn on top of all of the tools and techniques you need to learn. And so people who went through a PhD program typically have those types of tools, techniques, and knowledge. But with the democratization of tools and techniques, and with data science becoming more prevalent in today's world, it's now a job where people at all levels of background, partake and do it. And so as an undergrad who's trying to get a job in data science, it's really important that you have these theoretical foundations, whatever they may be, ostensibly the ones you learn in 40A and B, that will help you to do your job later on. So those are why we have these two classes. So here we have a bunch of images from MNIST dataset. This is like a very common, everybody here heard of MNIST dataset? Maybe a couple people. So it was like the first data set that you would use if you want to try and get into neural networks. You want to try and learn how to take a number and say, like, is this a 0, or is this a 1, or is that a 1? Is this a 9, or is that a 2? So you would train your machine learning model on this very tightly built data set, and then from there you'd be able to train a classifier that would tell you, from some probability distribution, if the number that I'm putting into a system like that is a 1 or a 2 or a 3 or a 0, so on and so forth. So the reason why I put this up here is not just because it looks kind of cool, but because really machine learning is all about trying to find patterns from data. And as a human, we can find lots of patterns from data, right? Like we might say that a pattern with 0 is that there's a big empty space inside, and this is like a closed uniform shape, right? Like that's not a 0. A 2 tends to have this, or it could have that. So like as humans, we observe patterns to us that make sense based on how humans learn. How humans learn, well, that's a problem for psychology and neuroscience. But what we can get out of this is that as a human, I might try and build a set of patterns that would help me to detect whether a number I've never seen before is a 0 through 9. For example, if the number has a closed surface like this, then it's not going to be a 1. It's very likely to be a 1, or very likely to be a 0, or a 6, or a 9, or an 8. But it's not going to be a 1. So the question is, we are very bad at doing this at scale, though, and we don't want to have a bunch of humans sitting around making predictions. We want to be able to have computers do that for us. So the question becomes, how do we take this notion of being able to detect patterns and have a computer do it for us? In order to do that, you have to take Python or whatever programming language you're using with a bunch of statistics and math, and build some sort of system that allows a computer to automatically detect patterns from data. So the things that you learn in this class will help you understand how that process works. And when you couple that with libraries and tools and programming languages, you'll have a much better time at understanding how computers automatically learn these patterns from this data. Because it's not quite so easy to determine what is it that the computer cares about when it's trying to determine the difference between a 0 and a 1. For humans, it's very easy. But for a computer, they might not even care about the structural difference of a 0 and 1. There might be other patterns, statistics in the data that it cares about that we would never even think to care about. So this is where it's kind of hard. We have to sort of learn how to speak the computer's language, which is numbers, zeros and ones, and math. Okay, so that's how we're going to kind of approach this course and why it's important. For this course, you can kind of think about it as broken up into 2 sections. The first one, which is roughly the first 3 weeks, is how do we optimize problems to solve linear systems of equations. So essentially, we're going to say, given some sort of data set, can we find an equation that represents some sort of line, and we can use that line for like a regression task. You might remember this as like y equals mx plus b. So we're going to be taking that, and we're going to be observing it through the lens of linear algebra and matrices, and how do you learn these lines when you don't necessarily are able to solve a system of linear equations. So things like using gradient descent. So we'll get into all of that in other lectures. But after this 3rd week, we'll quickly transition gears and go into probability, where we'll start to think about how do we use probability to learn from data. And that is leading us to something called naive Bayes or Bayes classifiers, Bayesian probability. For that, you might think of like a traditional spam classifier for email. How do you detect spam versus not spam? And a very classic way of solving that problem is to use Bayesian probability. So the 2 ways of doing machine learning, well, there's a lot of ways of doing machine learning, but 2 of the big foundational ways of doing it are through this idea of optimization tasks and regression. And another way of doing it is through these ideas of using probability and modeling your data to try and determine the probabilistic events of seeing a new piece of data. And so we're going to kind of go into both these fields or these sides of machine learning and learn about each of them, because that will set you up nicely for your future classes. Okay, and for the learning objectives, I'm not going to read these, but it's basically that you understand at the core of machine learning, there is this like kind of beating heart, and we want to observe what that beating heart is, and easily put that beating heart is math and computation. And so we'll do the math part in this class, and you'll do the computation part in 40B. But this will allow you to make use of 20A, 20B, maybe a little bit of 20C, linear algebra. We'll talk a little bit about, I guess anything that has a derivative is technically a differential equation. But you'll see some of those things when we talk about gradients. So you get to use a lot of what you've learned so far in your undergraduate career and possibly in high school in this class. So in that sense, it's kind of nice if you feel like you're doing well, because you can see the fruits of your labor paying off. So that's a nice part of it. If you ask DSC80 students what they have to say about DSC40A after the fact that they took it and they've gone through DSC80, they tend to like it. So that's good too. Okay. Any questions so far about like, the idea of why we're taking this class and why it's here? Okay. So as far as logistics go, like I said, see the post on Piazza, but everything you need is on the course website, and you'll turn everything in through Gradescope. The department decided not to pay for Ed anymore, so we're using Piazza instead of EdSTEM. So we can just kind of give this a big fat X. Yeah, there we go. So yeah, that's where logistically. I tend to do this class as a flipped classroom because I think it's, out of all the 20 series classes that I took as undergrad, sitting in class and watching somebody do math on the board wasn't necessarily the best way to learn it. And the field of educational research, as bad as it is, there's a lot of really good research to show if you do a flipped classroom approach for math, and you actually have in-class activities where people can work on problems and do things like that, it winds up being a very beneficial way of learning math. So that's the way I run this class, is through a flipped classroom. And probably the most important thing I can say about that is that you watch the lecture corresponding to the hops problem that you're going to work on before you attempt the hops problem. To make this easier for all of you, on the course website, we'll put by the hops problems like a little thing about which lecture you should watch before doing it, to make that easy for all of you. Especially not being like in the academic year, we're meeting up twice a week it can be difficult to figure out where you should be in terms of watching the lectures. So we will make that as easy as possible for all of you. And we'll also have a ton of office hours. It's typical, I would say, would you all agree, COGS or DSC40A staff, that DSC40A probably has the most people going to office hours of any class? They're all shaking their head yes.
Yes.
Thank you, Nick. That is what my experience has been as well. So, but office hours doesn't have to be about 48. You can also go and ask about grad school or data science as industry or career. We're happy to talk about any of those things, but we're also there for any help that you need in 48. There's also this practice DSC40A website. You can go there and see a bunch of practice problems from previous years, midterms and finals. I don't think there's any errors on them. There might be one error with the smoothing problem and probability, but I'm sure someone will post about that and I'll provide a response. I don't fix it because I don't run the practice site. And it was written in Python horribly, and the whole thing is like very fragile, and so whoever touches it is going to break it, and then they're there for 4 days and fix it. But beyond that, I think it's a pretty good site in terms of giving you guys extra practice problems, because that's one part of this class that's difficult, is finding problems to practice on to get ready for the exams. But we will make as many problems for you as possible. Okay. Any questions before we start with like the actual content of what modeling is and going into that part? Okay. So consider this case where you're trying to find an apartment in San Diego to live off campus, and it's horribly difficult because it's horribly expensive, and you're not able to afford a $4,000 apartment. So you decide that you want to move back in with your family, and you want to think about, how long is that going to take for you to get to school? Because maybe your family lives like 50 minutes away from campus. And so being the student that you are, you don't want to leave, 2 hours before class starts and then sit in class for an hour without, doing anything. But you also don't want to be late, right? Because who wants to be late for my class? Terrible sin. You'd never do that. So, you want to try and use your newfound data science skills that you have to look at a data set of maybe data that you collected from the first quarter of when you left class or when you left home and got to class. And from that data, which would look something kind of like this, you want to say, okay, when do I actually need to leave? Like here are all these departure hours, and you can say, like 8.45 is like 8:24 in the morning or something. Like 8.5 would be 8:30 in the morning. So you have your departure hour, you have minutes, how long it took you to get to class, and then you have the day that you left. Right? And this is very important because maybe for some reason there's some dependency on the day you left, which is actually true. If you leave going southbound on the 5 back to Pacific Beach where I live, on Friday you're going to run into traffic at 2 p.m. because everyone's like saying, screw this, I'm leaving work early. Whereas if you leave at 3 o'clock on Monday through Thursday, you're not going to really run into very much traffic going southbound. So day might have some sort of effect, and we want to be able to capture that in our modeling process. So this is kind of a task for machine learning, because we have our departure hour, what time we left. We have the ground truth, however many minutes it took us to get to campus, and we have the day that we left. So from this information, we can construct some sort of model and some sort of mathematical model that we can use. By mathematical model, I mean an equation. And that equation should have something where we can plug in, day of the week, plug in, departure hour, and the output of that should be how many minutes is predicting to take us to get to campus. And you might be asking, like, well, how do we put day into our mathematical model? Well, we can represent day as like a number, right? 0 through 6 to give us the days of the week. So a lot of things that we could do. Or we don't need to use day. If we want to do some sort of regression problem, maybe we just use departure hour, since this is a numerical scale, whereas days are a countable integer. So there's lots of opportunities that we have when it comes to modeling for how we want to actually do this. But at the end of the day, we needed to create some sort of mathematical equation to plug data into that makes some sort of prediction. So as a data scientist, maybe the first thing you want to do is look at a histogram of your data, because when we look at data from like an exploratory point of view, we can often learn about things. And we look at the distribution of commuting time, because that's a very obvious thing. Like, how long does it take us to get to class? Well, the average is probably somewhere around here, right? Where it takes maybe 68 to 72 minutes to get to class on average. We have some like weird data out here, right? Like maybe maybe here it takes a long time because you stop by Starbucks and you want to spend $8 on a latte, and it took you twice as long to get to class. So when we're doing modeling, we have to kind of look at the data very closely because, right, are you going to go to Starbucks every single time you go to class? If that's not true, then you might not want to include this type of data, or maybe like a flat tire or something. So these are things that we need to think about in the modeling phase, is where does this data come from, and what is I harp on this term a lot in all my classes, but the data generating process. Like, what is the physical process in the real world that generates this distribution of data that we see? Because we're trying not to write an equation that gives us this distribution. This is but a sample. We're trying to write an equation that gives us a way of modeling that data generating process. And so we understand that data generating process by taking samples of data and doing analysis on them. Okay, so another way I look at this is with a scatter plot, and we can see what time we left home. That's very important, and we see how many minutes it took us to get to class. And so we see some sort of like trend here, right? It looks like things are going like this, or maybe like this. Obviously, like this is not the trend, right? Like, would you all agree that's not the trend? So we know already if we want to have an equation that's a line, you might say like, remember y equals mx plus b, right? That's a line. We want to find some sort of line, any of these lines, that best represents this data. And it need not be a straight line either, right? It doesn't need to be like this. It could be something, like that. It could also be, that's not very good. But it could be a straight horizontal line like this, right? If we had a straight horizontal line like this, what would that be saying? If we use that line as our model for how long it would take us to go to get to class from leaving home, what would that line be telling us? And think about it in terms of y equals mx plus b. And when I say y equals mx plus b, what I really mean to say is y is our output, right? Like what time, however many minutes we think it's going to take us to get to class, and x is our input, what time we decide to leave, and you forget b. B is just some biased term for the y-axis, but m would be, of course, the slope of the line. So in this case, where we had a horizontal line, what would we be saying? What would be the way that we could think about these y's and x's? Because machine learning is all about inputs and outputs, right? Inputs to a model is our data, outputs are our prediction. So if we have this straight horizontal line, what do you guys think? Yeah.
At any time we leave, it just takes 80 minutes to get there.
Exactly. So this is what's called the constant model. And it's arguably the simplest model you could build. You just say, I don't care, whatever the input is to my model, you're always going to predict 80. And you might say, like, well, that's a stupid model, right? And I would agree with you. It's a very naive model. However, this can be a very good and useful model. The reason why this can be a very good and useful model is because whenever we're doing modeling, we always want to have some sort of baseline. We want to have some sort of way of saying, what is the most naive approach we could take that would yield a result that's somewhat realistic and probably better than just pure guessing? And so to build this type of model, we might want to look at the data and try and determine, is there some place where like a constant prediction, like maybe the average, could be useful? We'll look more at that in a few slides. But let's look real quick at what happens when we try and change this model by adding another dimension to our data, which is day of the week. And something kind of interesting. I'll use yellow to represent a model for Tuesday and Thursday, and I'll use purple to represent a model for Friday, Wednesday, and Monday. So if we want to draw a line for a reasonable line for Friday, Wednesday, and Monday, it might look something like that. If we want to build one for Tuesday and Thursday, it might look something like that. Does that seem kind of reasonable to all of you? Right? One question is, why do you think there's such a big difference between the orange and purple lines? Like, what is something that we can see in the data that's causing this big discrepancy between the lines? Why are they so different? Like, you can't tell me there's a difference between Monday, Tuesday, Wednesday, Thursday, and Friday for traffic, right? Like, most people who are driving the road don't have Monday, Wednesday, Friday, and Tuesday, Thursday classes, right? Like, most people are just going to work. So what's the difference between, like, why are we seeing this phenomena in our sample data set? And the answer is actually in the points of the data. So look at the actual data, and that can give you some insight. Remember, what did you do last time when what was the real reason why it took you a long time to get to class? What was that reason? Remember, you're driving to class, it took like double the time, 120 minutes. Why? You did something, you spent some money.
Starbucks.
You went to Starbucks. And now, not only did Starbucks cost you $8, right, that's bad enough, but now Starbucks is fucking your model up because you left Starbucks in there, right here, and now, for some reason, you're like, whenever I go to class on Tuesdays and Thursdays, it kind of looks like it takes me longer. Like, it makes this line that I'm trying to model data with different. A lot of it is because of these high points up here. They're causing us to, jack this model upwards because this model, has some sort of relationship with our data. And in order to make this line fit the data, it's got to pass through all these points in a way that makes it so that its distance from all the points, is kind of averaged out. And so that's why, because you have these points here, this line all of a sudden goes upwards versus we don't have any blue or purple or green points anywhere above here. So this purple line stays low. And so it's not to say that bifurcating your data into Monday, Wednesday, Friday, Tuesday, Thursday, and modeling them separately is wrong. A lot of times you want to build different models for subsets of your data because of specific reasons. But here we can clearly see that there's something off about the data that's causing us to see a pattern that is indicative of a pattern in our sample set and not necessarily a pattern in the data generating process, right? Going to Starbucks was something that you did. It wasn't something that's part of the data generating process. And so you can put anything in there, a car accident, ambulance, going to see an ex-girlfriend right on your way to class. Like, there's anything that you can put in there that will cause a disruption to the data generating process pattern. And that's noise. We want to try and work with that noise and reduce it as much as possible when you're modeling, because all this noise has effects on your data and on your models. So you're all tracking so far? It's pretty reasonable? Good. Okay, so we already kind of talked about this a little bit. Yeah, talked about that. Okay, so we talked about some possible models, right? I'm going to list a couple of them out. You could have something like this. We could have the constant model. We could have some sort of quadratic model. I suppose we could have something like this as well. So there's all sorts of things we could do. Like, these are the range of models we could have, and it's kind of up to us as the data scientists to determine some way, like, to evaluate all these models and compare them and figure out which one is the best for our given data sets. And that's kind of like what a large part of this class is going to be, is trying to determine what's a good model versus what's a bad model. Because a bad model, like this one, is completely useless. Arguably, these two are probably very similar in a lot of ways. This being a much more complex model because it's got some quadraticness to it, and this being a very simple linear model. But by and large, they're very close compared to how off this thing might be. Okay, so in order to determine how we want to determine how good a model is or isn't, we have to have some way of representing it mathematically, and we do that using this idea of like an error. So if we have let's say we have a constant model, which is right here, and I want to say how far apart is, this point from that model, that line, I have to take some sort of distance measurement, right? So we're always wanting to determine for any of these points, and maybe I'll spell this out a little bit more. Any one of these points is like x sub I, y sub I, right? Because it's coordinate, it's like home address on this coordinate system. And I want to take this data and I want to try and figure out how far away it is from our model. And what you're going to wind up doing over time is you're going to take your model and you're going to start to kind of shift it, right? Up or shift it down. So you might change it like this, or you might change it like that. And that change to your model winds up changing all those distance calculations. And what we're trying to do is take all of our distance calculations and sum them up somehow and then see like what the average distance is from all our points to our line. And perhaps the line which minimizes some sort of distance would be the best line for that data set. Now that comes like a lot of preconceived notions and difficulties as you go up and add more attributes to your data set. But this is primarily the thing that we're going to be working on in class, is finding some way of taking a line and fitting it to our data that makes for the best predictions possible. And honestly, that's most of what at least machine learning is from a regression point of view, where you have a line and a line is continuous, so I can look at any single point of this line and know exactly, well, not this line, but this line, I can go here or here or here or here, and I can figure out exactly how long it will take me to get to class. So the line represents just a continuous generalization of our data set. I guess is one way you can think about it. Okay, any questions so far? Okay, so one way to think about our line is that it really represents a hypothesis function where we're trying to say that we have this function h of x, and it has one parameter in it, and that is h. And here we have three different hypothesis functions. One which predicts the constant model at 60, one at 70, and one at 100. And we're looking to say, given any input of x, right, like for how long it takes, or any input of h, what is our x going to be? So for any of these inputs, it's always going to predict 60. And for any of these inputs, it's going to predict 70, so on and so forth. So this idea of a hypothesis function is very general, and we're going to use it to kind of act as the standard for any type of line that we could draw. But this is kind of the step that we're trying to build here, is to reason about how we can mathematically define a line and define its inputs and outputs. So in this case, we still have a hypothesis function, but instead of being the constant model, we have a linear regression model of the form h of x equals w naught plus w sub 1 times x sub 1. And this model has two parameters, w naught and w sub 1. And in this case, w naught is just where it crosses the y-axis, and then w sub 1 is the actual value that we're going to use to input to make a prediction. So that's like x would be, well, here's a better way to say it. So w sub 1 is going to be our slope, and w sub naught is going to be our y-intercept, and x sub 1 is going to be the data point, right? Like all these, it could be any of these little data points, but it'd be really any point along the line. And from that, we will get an output. And that output, which would be our prediction of how long it actually takes us to get to class from home. So here we're saying that our hypothesis function just represents the equation of a line. And the equation of a line has certain parameters, right? The parameters being the y-intercept and the slope, and then an input, which is a piece of data, an x, what time we're leaving. And the reason why we have these weights, w naught and w sub 1, is because w naught and w sub 1 change. They change based on whatever our line is. So this y-intercept and this slope for this line is different, of course, than this one or this one, or this one. So the reason why we have those variables in there is because it allows us to represent any line, right? The infinite number of lines that we could draw on, this plane here. It allows us to represent any line, and X represent a piece of data that we put in. And with this type of way of modeling data, we have a way to quickly, maybe from like a computational point of view, right? If I want to write a program to find what the best fit line is, that would be optimal. Because if not, you're going to spend arguably a very long time coming up with different random lines and then plugging them in and seeing how well they do. What we need is some sort of way to model this so that we can really have a computer figure out the best fit line for us in a very fast way. And there's lots of ways to do that. But it all starts from having a general form of the equation and using that to be able to plug in the attributes of that equation as well as individual data points to test how good the prediction is. Because at the end of the day, we can certainly find a line that represents the data that's best for, represents a model that's the best for the data that we've collected. But what you really care about is not modeling this data, right? Like that's a consequence of the problem you're trying to solve. But the real problem you're trying to solve is to predict how long it will take you to get to school tomorrow, right? You won't actually know how long it takes you to get to school tomorrow until you leave at a certain time, but you're trying to predict that. And so you only have the historical data to look at. So the real problem you're trying to solve is a prediction problem. And to do that, you have to solve this first smaller problem, which is to build a model. But your model could fit the data very well, but maybe tomorrow they open up a new freeway, which cuts your time in half to get to school. Now your data set's kind of useless because it doesn't represent the real world data generating process anymore. So your data, the sample data, has to mirror one-to-one very closely with what's going on in the real world and be a very good sample. If not, the model that you build, no matter how good it is for the data you have, is going to be useless for the problem you're actually trying to solve. So a lot of people who do machine learning lose sight of that idea. They think that they're just trying to build a good model for the data that they have. But you don't really care about your data. You care about the unseen data. And that's where the difficulty is. You have to reason about that unknowingness. And be also fine with the fact that your model is going to perform always worse on unseen data than on data that you have. Because the data in the real world comes from a population which has a much wider variance than the data you've collected from your sample set. Any questions so far? All right. So let's talk a little bit about the constant model. I can go through this because we already did a bunch of it, but that's just this line here, which represents for any value that I input for departure time, I'm always going to predict 80. Constant model, really like the best one you can build, it's going to be a model that probably follows the average. Like this is a better model than this. Like we all agree on that, right? There's no worry about that. Maybe Reed's looking at me like you're crazy. Like, are you sure, Reed? Like, this is definitely the better model. Okay, so so you're using kind of what's called in this case a heuristic, and the heuristic that you're using is that I only have one attribute to define my model, and that attribute is how many minutes it took to actually get to school. And so the best prediction you could possibly make is just take the average, because that's the most likely occurrence in your historical data, and therefore, barring no changes to the data generating process, it's most likely to be the same outcome tomorrow and the next day. Over time, that will change, but that's a good kind of heuristic to use when you're doing modeling. The only other one you could probably think of in this case, you'd probably want to use you probably want to use the median instead of the mean, because we have some data out here which looks like it could be outlier-ish, maybe. And so the mean might be, or the median might be like this, and the mean might be over a little bit. So the median might be a little bit better because it doesn't care about these things. Anyways, the constant model just figure out which line is best, and we have to have some sort of heuristic to apply to that. Let's see. So This is not too bad. Imagine we had five points in our smaller data set. The prediction for using the constant model would just be no matter what, 72, 90, 61, 85, 92. So if we wanted to determine what the constant model for this data set to be, we would have to have some way of representing the average. So we would just take the average of all of these data points and then subtract them from each of the individual points, and then we can get our average from that after dividing by the total number. And so when we have these kind of very simple heuristics, it's very easy to come up with a model that uses the mean or the median or the mode or any number of these kind of what we call summary statistics of our data set. Let's see. So yeah, in this case, I mean, mean, median, you probably are all familiar with that, I guess, at this point. So I won't harp on it for too long. But the question has become, calculating the mean and the median, because this is easy to calculate. In fact, anything is easy to calculate compared to determining which one's better, the mean and the median. So that question of is there a best prediction we can make is a very charged thing. It's very difficult to kind of think about what the best might be. Are there some other summary statistics besides the mean, median, mode that you guys could think of that you could use? So what are some other ways to summarize data sets that give us one value? Yes, Nick?
If you wanted to, you could use the max.
You could use an max. In this case, you'd be saying 92 is what we should always predict, right? Do you guys think that'd be a good predictor? Why not?
Is that upper limit?
Exactly. 92, I'm sure, occurs, but it probably doesn't occur as often as 85. And again, we're not trying to predict actual numbers. We're trying to take of the range of times it takes to go to work. We're more likely to find a time that's closer to the mean or median than something that's like the max. And there's lots of other things we can take too. Any other ones you guys think of? Maybe think about like interquartile ranges, stuff like that. What could you blend the min and the max to create another heuristic?
Min plus max divided by 2.
Yeah, you could do that. You could also take the in between the min and the max. There's lots of things we could do. And the question becomes, which is best? And that's really the thing that matters most. Honestly, like DSC 885 is quite a bit, right? When you think about like how long it takes and how far you're off of. So these are very easy heuristics to calculate, but they're very difficult to determine which one is the best. And that determination of best is often going to be based on the sample data that you've collected, coupled with the domain knowledge of you in this situation. So if you're like, on any given day, there's like a 1/4% chance I'm going to go to Starbucks. Well, you might want to take your sample data set of maybe 1 week where you did go to Starbucks once. You might say, maybe I want to include a little bit more likelihood of me going to Starbucks, and so I'm better off taking the median because it's a little bit closer to the average value of how long it'll take me to get to class because I'm likely to go to Starbucks, some amount of time. So these are, the whole idea of modeling isn't just purely like a mathematical exercise. It really requires a lot of refining of the problem based on what you know about it and domain expertise. If maybe you taken Cogs 9 with me. Okay. So you imagine like how important domain expertise is, at least to me. Maybe not to some other faculty members, but I think the domain expertise is probably the most important part of all this. Way more so than any of the math or computing stuff. Knowledge about a problem in the domain is very, very important. Okay, so the cost making predictions, we have to have some way of quantifying costs. We do that using what's called an error term, and This is just taking one of our y sub i's and taking our hypothesis function, and we take these two things and we subtract them, and then we get an error term. And that error term we can use to determine how far off we are from an actual value. So if we know that it took us, let's say if we're looking at the data, it took us, maybe it'd be better to go to a plot. All right, so let's say that we have our constant model, and for our constant model, we know that if we left it at this time, it takes us this long to get to class, but we predicted 80, and so our error would be 20. So we would say that, okay, 20 is pretty egregious. It's 25% wrong off of our 80 minutes that we guessed. And so we have to have some way of quantifying these distances, because once we can do that, we can use those distances, like I said, to change this model and make it better and fine tune it. Because if we had that as our model, this error term would be much, much less. And by model, we use this hypothesis function here. We're just saying, given some sort of data input, what time we leave, our hypothesis function does some sort of math, right? It's our algorithm, our equation of a line, and it outputs some answer, some prediction, and we take our actual value and subtract that from our prediction, right? We take our ground truth and subtract it from our prediction. We know how well our algorithm is working for that one point. Another thing that you can do is squared loss. Squared loss is a very nice thing to do. Anybody know why we do squared loss, or can think of why it'd be important? And what I want you to think about is the symmetric nature of data around your prediction. So if you predict that it takes 80 minutes to go to class, in the real world, it's going to take you certainly more than 80 minutes, and it may also certainly take you less than 80 minutes. So your predictions will be both above 80 and below 80 based on your hypothesis function. So why would we want to square our error? Yes?
To make both sides be like positive so you know how much the error is.
Exactly.
But from that, I have another question. Why
Sure.
this is absolute value?
I mean, you can certainly use absolute value. In fact, absolute value is one of the other secondary ways that you do this. Squared loss is used for something called mean squared error, and absolute value, bless you, is what's used in what's called mean absolute error. So mean squared error, mean absolute error. These are kind of the fundamental ways of doing this. Squared error is very nice. It has some nice properties to it that you'll see in future lectures, or the next lecture. And really it allows us to have a differentiable function. So remember when I said that we have some sort of line that we're trying to predict, and then we change that line over time based on new types of values for our slope and our intercept? Well, the way you come up with those values is by trying out a bunch of iterations. And when we're doing these iterations, we're trying to solve we're usually trying to do what's called a convex optimization problem. And so having squared loss is very nice because it gives us a convex function to optimize on. Whereas if you mean absolute loss, you don't get a convex optimization anymore. But we'll talk about that in a little bit. So we have this way of defining squared loss, and that's really just this is equivalent to this, and just removing the hypothesis function because it's the constant model, so it's just going to be h always. There's no math going on. You're just going to pick h. And so we take our prediction, we take our ground truth, we subtract them, we square it, and that gives us our squared loss. And a loss function is just something that's there that helps us to calculate what that error is. That's all it does. And you can have squared loss, you could have absolute loss. You can build your own custom loss functions that do crazy, miraculous things. But at the end of the day, your loss function is just some way of quantifying what that error is between your model and what your prediction, what that model is predicting, and the ground truth. Let's see. So Yeah, this we can kind of skip over. Let's go here. Okay, so averaging squared loss. Here we take for that small data set that we had before, it's the same one here. We have these values. And we want to have some way of calculating errors. So obviously we can take like 72 and we can plug it into here and we can have our ground truth or we have our ground truth and we can plug it into our constant model and we can subtract them. And what we get is, here's how long it took to get to class. And here's what we guessed. Here's how long it took to class. Here's what we guessed, right? Because it's the constant model. So it's always going to be the same guess regardless. And we do that. We do a bunch of these squared loss functions, right? One here, one there, one there, one there. And this is just of the form, y sub I minus h squared. Y sub I, because this is the ith data point that we have. So in this case, this would be really y sub 4, y sub 5, y sub 1, and so on and so forth. So we do this whole operation of calculating these individual errors using this loss function 5 times in a row, and then we add them all together, and then we divide by the total number of data points that we're trying to make predictions on. So in this case, we have 5, so we multiply it by 1/5, and that gives us a value right here, 163. And what that value is, it's the average of squared loss. It is now a statistic that we can use to quantify how well our constant model works when we use the median 85 as our constant model. And we get the median 85 by taking the median of all these numbers. If we take the mean of all these numbers, right, these 5, we get 80 instead of 85. If we use 80 instead of 85, and we do the same operation of mean squared, or this mean squared error. I know it's confusing because we're using the mean, but it's being used in mean squared error and median, being used in mean squared error. Median and mean, these things are just the constant model. We're using a heuristic to pick a constant model. And then in these squared losses, we're taking that constant model's prediction and then subtracting it from the ground truth, and then we're multiplying it by 1/5 to get the average, and that gives us these statistics here. So we have 163 for using median as the heuristic for our constant model, and we have 138 as using the mean as the heuristic for our constant model. So which is better, 163.8 or 138.8? Any ideas? And I'll give you guys a hint. You got a 50-50 chance of being right. So if one person wants to guess, I can guarantee you that the next person to guess has a 50-50 chance of being right as well. So what do we think? Yes?
So 138.
Why would you think 138?
We're calculating how much it deviates from our predicted value, and the sum of the mean sum of squared deviations is 138 as opposed to 163, so it's less.
Exactly. That's perfectly right. And a very well way of saying it is that the average squared error, or loss in this case, for our mean as our constant model is lower. It's 138 versus 168. So we would say, based on this heuristic that we're using, 138 gives us a model, right, a line which has lower loss overall. And so we would say that the constant model, using the mean instead of the median, is a better model for us to use. And if we go way back over here, right, and we say that this is the mean and this one is the median, I forget now. Yes, the mean is better. So we're saying that for our data, the mean is better. And that makes complete sense because in our sample data set, we have these values out here which are contributing to our mean, being a little bit higher than the median. And so when we take the error rate, I know that was using a sample data set, but if we were to apply this back to our original data set, pretend like it's the same thing. The reason why the mean is doing better, the mean is doing better than the median is because we have these kind of like maybe outliers, or what could be considered outliers maybe in the data set. And so when we calculate total error, those points out there prefer the mean over the median. And so you get less error. And these things contribute a whole bunch of error. Imagine taking 130 and subtracting it from, like 75 versus 70. That's, adding 5 extra error points, if you will, to our total error. Even though it's being averaged, it still winds up being more. So, any questions so far about this how we're using the data and these models, and then this idea of loss to try and quantify the goodness of a model? And don't think about loss functions so much as telling you what model, like, we're not using a loss function to determine if, like, it's not, for just a line we're trying to predict, this line versus that line, loss function isn't really telling us which of those lines is better for, like, a regression model. It's not going to tell us whether this is the better line or that's the better line. The loss function is giving us a way of taking different models. I know obviously these are both horizontal lines, they look the same, but these are separate models and they're allowing us to compare them and determine which one is more appropriate for our data set. So you can think of it as a way for figuring out which of the slope and y-intercept is the best for our given data set. Okay. So mean squared error, average squared loss. Yeah, so I already said this is what's called mean squared error, and this is average squared loss, mean squared error. Mean squared error is a loss function, but people use it people use it to define the mean squared loss for your model. And in this case, this is just, I guess it's kind of good to go over. Okay, so in this case, R stands for risk as an empirical risk. And it's a term that comes up quite a bit because when we talk about the risk, we're not necessarily talking about the risk of an individual data point. Like mean squared error really is talking about these little errors right here. When we talk about empirical risk or risk, we're talking about all the error as one. But people use MSE to talk about this term right here, like the total amount of risk. But in reality, this is really the risk. Like this has less risk than this model, but people use mean squared error to define that term. But really, it's risk. Anyways, these are just like small things. And you can see if we put in like a large number, the risk goes way up. And it doesn't go up linearly, right? It doesn't, like 100 is, a little bit more than 80, but 538 is way more than 138. Now, why do you think that number shoots up so much? Why don't we have this kind of like, yes?
It's quadratic.
Exactly, because we're taking the squared error. And so by using mean squared error, we wind up having a large penalization to our risk factor. We're saying that if you have maybe some outliers in your data, which is causing you to have a lot more higher mean squared error terms, then your risk goes way up, not linearly. So that would be a good reason why you might want to use mean absolute error instead of mean squared error, because you don't have that squaring term anymore. If you have 100 and you're using mean absolute error, this risk would obviously be way lower. However, there's a lot of benefits to using mean squared error, like I said, which we'll go over. So in machine learning, everything is a trade-off. You're always making trade-offs based on the complexity of modeling it, the complexity of the data that you have, and decisions that you make have to kind of, you have to keep those things in mind. All right, so visualizing mean squared error. Here we have a bunch of errors. And really, this is we have a bunch of parabolas here for these terms, and this one parabola is the average of all of these together. And what we're trying to say is, let me just erase these real quick. And so what we're trying to say is, at what point do we have the best model, right? And that point is the vertex of this quadratic function, which is right here. So wherever this point is, which is going to be that's our risk. And at that point, where our risk is lowest, that's going to tell us which parameters, or in this case, which constant model is the best one to use. So really, if we have mean absolute error instead of mean squared error, we would have something that looks more like, this. And so immediately you can tell that the possibility for the total amount of risk that you can have goes way up when you're dealing with something that's quadratic, than you're dealing with something that's linear. So, but this quadratic equation is much easier to minimize because, we can take tangent lines everywhere along this curved surface till we get to the very, vertex. So we can figure out what that bottom vertex is much easier. Or in some cases, depending, this bottom of your mean absolute error could look like this, in which case there'd be an infinite number of solutions to that problem. So there's, like I said, it's all about trade-offs, and go much more in depth into this in lectures, but just kind of set things up for you. Let's see. So the mean squared error in general, if we're using things like this term, but in reality, you're always going to see it as, written something like, 1 over n summation of y sub I minus x sub I, or here it could be your hypothesis function. So that's usually how you're going to see it written, and in all the homeworks and stuff. Really, whoops, I should put the square up there. So that's. I mean, mean square is not very, like this type of stuff. Mean square error, mean absolute error. I don't think the math behind these things are what's complicated. I think the complicated thing at this point is wrapping your head around the use of this as a way to calculate error, and then using the summation of all these little errors to come up with your risk, and then how that applies to you making a better model or a worse model. Remember, this is your risk. That's really confusing. I wouldn't worry so much. I'm not going to care whether you guys refer to like this individual thing as mean squared error or this whole thing as mean squared error, because everybody prefers this whole thing as mean squared error. So I won't put that there. This is perfectly fine. Usually you'll see something like that. Okay, so like these two things are, for all intents and purposes, interchangeable. But yeah, I suppose I should be fancy. Again, this is H here, not because in the constant model we just had some sort of prediction, but really you put your hypothesis function in there, which tends to be much more complicated. It could be a constant model like H, or it could be a line, but that's where you're always taking your ground truth and subtracting it from what your prediction is of your model. So yeah, this idea of, I'll say one last thing too, is in this case, H star, whenever you see the word, like the notation of star here always means the best of something. So the H star that we're trying to figure out is the one that minimizes mean squared error. So if we're looking at 100 versus 80 or 85, so far, of all these, which one is H star? That's not a trick question. Yes, exactly. The mean, that one is what our H star would be. We would say so far, that is our best one. However, since we're using mean squared error, we have this sort of convex optimization problem where at the vertex, it will tell us exactly what the H star is. See, in this case, the mean absolute error, you could have infinite H stars, depending. Okay, so yeah, that's what we're always trying to do for best prediction. Next time, in next lecture, we'll talk about this idea of the modeling process. So everything you do in class, as far as the first 3 weeks, is going to be centered around the idea of choosing a model. It could be the constant model, it could be a regression model, it could be a quadratic model. Choosing a loss function, mean squared error, mean absolute error, some custom loss function. We won't go over custom ones, but you'll see things like 0, 1 loss, mean squared error, mean absolute error. And then you'll try and minimize your equation, your model, along with that loss function that you have to find the best parameters for that model. And then that's how you'll find the best model. So if you want your model to be y equals mx plus b, you're going to use the loss function that you've just determined, mean squared error, mean absolute error, to find what that best m and that best b are. And once you found the best m and best b are, based on your data set, then you will have solved this problem. Find the best model, your H star, based on these three criteria. Okay, so any questions on this stuff? Not too bad? Okay, you guys have any questions? Or read and look at you? No, it's good. Okay, so why don't we take a, okay, so the way this will work is I've got this 25-page linear algebra bootcamp packet. There's no way in hell we're gonna get through all this, even if we had all 3 hours. So we'll take like a little 5-minute break. I'll write some key takeaways on the board that you should walk away from. Like, you should know what those things are, and if you don't know what those key takeaways are, then you should go through this packet that we're gonna give you later today or tomorrow morning, and make sure that you review your linear algebra. Like, linear algebra, you guys are pretty good, or it's like, 18 wasn't that great of a class. Don't lie to me. I went through 20F, same thing with 18. It was horrible. But you guys, like, you know, been through linear algebra once maybe, right? Or have you been through it maybe a couple times? I've been through linear algebra like 4 times now, so. And not because my own choosing, I'll tell you that much. But it's one of those things where you continuously repeat the same material in all these classes. So you're gonna see all this stuff constantly. But in this class, if you don't know this stuff, you will fail. Like, you will get bad grades if your linear algebra is not very good. So we're gonna kind of walk you through the things that we think you should know, that we have time to go through, and then you should go through this packet and make sure you understand everything. Because if you don't understand these things, it becomes very difficult when we go and we move from something like the costed model to a model where we have multiple attributes. And now we have to represent our model using matrices, right? And so, like, doing these kind of operations on matrices and stuff really complicates things, especially optimizing functions in high dimensional, places. So we want to make sure that you guys have the appropriate linear algebra stuff. And then the TAs and myself will take turns as kind of, this will be like a discussion. It should be a friendly discussion about linear algebra, and it shouldn't be hostile, or it shouldn't make you feel, bad. If you don't know something, that's great, because now you know what you need to study, right? So uncovering your issues is always a good thing. So yeah, I'm going to take like a few minutes, and then we'll get set up here, and then we'll begin. I suggest walk around a little bit, stretch your legs, chat with the read for a few minutes,